Well, today your challenge in class was to create a box that had a maximum possible volume. And it was really interesting to see all the different approaches that you had and the thinking that you were using. Some of you were so desperately trying to use your calculus and decide what length of square you would cut from your cardboard in order to create the maximum volume. Well, today what I'm going to do is I'm going to show you how to think through problems like this using a protocol and an organizer so that you can gather the information and be able to use your calculus skills to solve these types of problems. So the problem that, excuse me, I always do that kind of thing and erase that mark. There we go. Okay, go back to the hand. Here we go. Okay, so you have this graphic organizer in front of you, and we are going to use this protocol to kind of explain the process of how to solve a problem like the one you did in class today. So the first thing you always want to do is you want to figure out, well, what is the question that you need to answer? And so the question for this problem was, what are the dimensions of the box? So we know a box is three-dimensional, so we are going to have to find the length, we're going to have to find the width, and we're going to have to find the height of this box. Okay? So next, after we find the question, we're going to move on to clarify. So clarify just means make clear, what are the facts that are given to you? Well, we had a piece of paper that was 8.5 by 11, and we also know we're going to find volume. And volume of a box is a formula we know, length times width times height. Okay? Well, in looking at this, I kind of draw a diagram to kind of better understand what's going on here. And in this diagram, I am going to cut squares from each corner of the box to create my three-dimensional figure. And I know that we have a length here of 11 and a length here of 8.5. Okay, sorry, I'm kind of getting used to my pen here. Now, I'm going to cut a square out of each corner. And since it's a square, it's going to be x by x. I'm going to cut from each corner. Okay. Now, in thinking of this, we have to decide what length, width, and height will be in terms of a single variable. The reason why we want to write an equation in terms of a single variable, because I'm wanting to find maximum volume. Well, and we've been studying how to find maximums. Maximums are found by looking at the first derivative and setting it equal to 0. So can't I do the same thing here? Is write an equation using one variable. So let's use x, and x will represent the cutout, or in other words, the height of the box. Now, if x is the height, then what will be the length? Well, the length then is going to be, notice I'm cutting x from one side and x from the other side. So actually I'm cutting out 2 x's. So it'll be 11 times 2x. And then the width is going to be 8.5 minus 2x. Okay? So our equation then for volume is going to be x times 11 minus 2x times a quantity 8.5 minus 2x. Oh, I'm running out of room, aren't I? There we go. Okay. Well, great. Now we know to find maximum, we are going to take the derivative of that and set it equal to 0. So I'm going to expand my space here so I have more space to write. I think I'll make my pen thickness a little less thick. Okay. So we have to find the derivative. Well, let's first expand this polynomial. So if I multiply it out, I'm going to have 11 minus 2x. Oh, good grief. Eraser. Okay, try that again. So originally I start off with x times 11 minus 2x times 8.5 minus 2x. So let's expand so that we can then use the power rule. So I have 11x minus 2x squared, okay, times 8.5 minus 2x. And then multiply once more, and I get 93.5x minus 22x squared minus 17x squared plus 4x cubed. Okay? And if I combine like terms, I end up with 4x cubed minus 39x squared plus 93.5x. So now the derivative of this is 12x squared minus 78x plus 93.5. So we end up setting this equal to 0. And now this is not a factorable equation, so I would have to use quadratic formula or graph it in my graphing calculator and calculate the 0. So when I do that, I find one critical number, and that critical number is 3.04. So many of you in class today did a great job. You estimated that you would cut out 3 from the corner of your box to create the maximum volume, and that was very correct. Now, how do I know for sure that's a maximum? Well, we can tell that by checking into a sign chart to see if the first derivative changes from positive to negative. Or looking on the graph, you'll notice that the graph of the first derivative is positive and then changes to negative at that value. So then if we estimate then approximately this to be 3 inches, we're going to cut, then our height will be, just 1 minute, I'm going to pause my video. So then our height that's the height is 3 inches, okay? So then the length is going to be 11 minus 2 times 3, which is 5 inches. And the width will be 8.5 minus 2 times 3, which is 6. So we end up with 2.5 inches. And when I multiply these dimensions together, I get a volume of 37.5 inches cubed. Exciting! Woohoo! We did it. Okay, now in looking at the protocol, we have to interpret the results. In other words, did we answer the question that was asked at the beginning? So the question was, what are the dimensions of the box? Yes, we found those 3 dimensions. Did we use correct units? Yes, we did. Now, is the answer within the domain? So in other words, if I cut 3 inches away from the sides, am I still within the domain? Yes, I am. Congratulations! Many of you found this area. Now you can see how derivatives are used to find that together. Okay? So this example, we have to find the dimensions of a rectangle, and we have an area of land that's inscribed by x-axis and the y-axis, and the graph of y equals x8 minus x cubed. Okay. Let's tackle this. We've got, so let me move this up a little bit here. So get out your protocol, turn it over, you should have 2 sides, and let's answer the questions that are asked of us. So first of all, what is the question we have to answer? Well, we have to find the dimensions of a rectangle with the largest area possible. So maybe we have a plot of land and we want to build a building on it. We want to make sure we maximize the land to its most potential. Now we are given that we're bounded by the x-axis and the y-axis and the graph 8 minus x cubed. So you can see for this I have a graph of this, and we can see that we're going to want to build some kind of rectangle within here. So something like this within this plot of land, okay? And we want to find the rectangle that is maximized. Now, when we do this, then we always are going to write an equation in a single variable, and the reason why, then we can take the derivative and set it equal to 0. So area of a rectangle. We know that area of a rectangle is length times width, or length times height, whatever you want to talk about. So for my rectangle, if you notice, the length here, or the base of the rectangle, is going to be x. Now, what is the height of the rectangle? Well, the height of the rectangle is determined by the function 8 minus x cubed. Okay, so if I were to define my variables, then x is going to be, we'll call it the base of the rectangle. And then the height of the rectangle will be 8 minus x cubed. So to find area, we multiply base times height. So the area then is x times 8 minus x cubed. So if we were to expand that, we get 8x minus x to the 4th. Okay, well, let's take the derivative and set it equal to 0, and then we can find our critical points. So I'm going to expand my work area here. So the derivative then of area will be 8 minus 4x cubed. Let's set that equal to 0. So I subtract 8 from both sides, divide by negative 4, take the cubed root. So the cubed root of 2 will be the base of my rectangle. Fantastic. Now, we would always want to check to make sure that truly is a maxima and not a minima, and we know that we can do that by looking at a sign chart. So if you were to do a quick first derivative sign chart and test it out at the cubed root of 2, we would see, like, if we plugged 1 into the derivative, the value would come out positive, and if I plugged in 2, it's going to come out negative. So yes, I do have a maxima. So if that is the base, then the height is going to be, so the height will be 8 minus the cubed root of 2 cubed, which is 2. So 8 minus 2 is 6. Now 6 what? What were the units of this problem again? The units were, whoa, I don't know the units. So if units are not given, I do not have to express my answer in units. So height is 6. Whoops, I have to switch back to pen mode. Height is 6. And then the base is cubed root of 2. Okay, now let's verify, make sure that we've answered everything. Did we answer the question? Yes, we found the dimensions. Did you use the correct units? Units were not given. Is it in the domain? Yes, so if we plugged cubed root of 2 into the original function, it is within the domain. Wow, fantastic work. Now what you need to do is you should have both sides of the protocol filled out, and then access the Google form, and please put in your answers to the even questions in the Google form, and then answer the 2 reflective questions about how we go about using derivatives to optimize a problem.